Good morning, everyone. My, my name is Rahul Verma, and my topic is external data representation and marshalling. External data representation and marshalling. At language level, data are stored in data structures. At TCP/UDP level, data are communicated as messages or stream of bytes. Hence, conversion or flattening is needed. They are converted to a sequence of bytes. What is the problem using conversion? Different machines have different primitive data representations. Integers. They have big endian and little endian order. Float type. Representation differs between architectures. Either both machines agree on a format type or an intermediate external standard is used. External data representation, an agreed standard for the representation of data structures and primitive values, whose example is CORBA, Common Data Representation for Many Languages. What is marshalling? Marshalling often is a process of taking a collection of data items and assembling them into a form suitable for transmission. Unmarshalling is disassembling to original on arrival. There are three alternative approaches to external data representation and marshalling. CORBA's Common Data Representation, Java's Object Serialization, and XML. Marshalling and unmarshalling carried out by middleware layer XML software is available for that. Although we are interested in the use of external data representation for the argument and results of RMIs and RPCs, it is a more general use of representing data structures, objects, or structured documents in a form suitable for transmission or storing in files. In CORBA's CDR, there are 15 primitive types: short, long, unsigned short, unsigned long, float, double, char, boolean, octet, any. Constructed types. There are sequence, string, array, struct, enum, and union. Note that CORBA does not deal with any objects, only Java does. And then there are different representations for the types used for sequence, string, array, struct. Now we can have an example of how it works. This figure shows an example of a field containing three fields of a struct whose respective types are string, and unsigned long. The figure shows sequence of bytes with 4 bytes in each row. For simplicity, we assume that each character occupies just 1 byte. Variable length data is padded with zeros so that it has a standard form enabling marshal data or its checksum to be compared. Note that each unsigned long, which occupies 4 bytes, starts at an index that is a multiple of 4. The figure does not distinguish between the big and little endian ordering.
First, let's look at how we can reduce the overhead in marshalling the arguments and the data copying. Just to jog your memory, marshalling refers to the fact that the semantics of the RPC call being made between the client and the server is something that the operating system doesn't have any clue about. So in other words, the arguments that are actually passed between the client and the server has semantic meaning only between the client and the server. The operating system has no knowledge of it. And therefore, marshalling is the term that is used to say, let's accumulate all of the arguments that is there in the call and make one contiguous network packet out of it so that we can give it to the kernel and the kernel can send it out. That's what is being described as marshalling. And the biggest source of overhead in marshalling is the data copying that's going to happen. And I'll explain that in a minute. Potentially, in doing the marshalling, there could be 3 copies involved. Where are these 3 copies coming about? Well, first of all, the client is executing. When a client is executing a procedure, all the arguments for the procedure call that it wants to do is living on the stack of the client. And there is an entity, we've introduced this terminology even before, called the client stub. And the role of the client stub is to take the arguments of the call which are living on the stack and convert it into a contiguous sequence of bytes called an RPC message. So the RPC message has no semantic meaning. It is just a contiguous string of bytes which you can pass to the kernel, and the kernel can then send it out on the wire, just like any other message. So that's the first thing that the stub does, and that's the first source of overhead. The client stub is making the first copy from the stack in order to create an RPC message. Now remember that the client is a user program, so it is living in the user space outside the kernel, and so this RPC message which has been created by the stub, it is part of the client's address space which is living outside the kernel. So this RPC message is in user space, and the kernel has to make a copy of the RPC message from the user space into its own buffer, the kernel buffer. And that's the second source of overhead, the second source of copy in doing the marshalling of the arguments. So now it is in the buffer of the operating system kernel. Now the operating system can kick the network controller and say, hey, go ahead, take this buffer, send it out on the wire to the desired destination. And the network controller at that point is going to move the bits from this buffer, which is in the system memory of the operating system, into its internal buffer using DMA. And this is the third copy that is happening. The copy that is done by the network controller using DMA to move the bits of the RPC message copied from the user space into the internal buffer of the kernel, and now this movement is being orchestrated by the hardware to move it from the kernel buffer into the internal buffer of the network controller so that it can then get out on the wire. So those are the three copies involved in marshalling the arguments of the call before it can be put out on the wire. And
At last, these are the references where you can look up to regarding the external data representation and marshalling.